Greetings to you. We are going to start the next session of our course on electrochemical techniques on pollution monitoring, and that will be module 4. In this module, we are going to study several electrochemical analytical techniques. So, they include electrogravimetry, conductivity, polarography, potentiometry, and several other electroanalytical techniques, which will help us in the day-to-day monitoring of the effluents, especially for pollution control. And unless we understand the basic principles of the techniques, we will not be in a position to interpret the results. That is why our approach in this module would be to understand the basic theory and then instrumentation and then applications as and when possible. So, after some time what we are going to do is we are going to solve some problems to make you more familiar with the concepts that you have already learnt. Okay. So, let us start with the electrochemical techniques. That is, first thing what I want to talk to you is about the electrogravimetry. So, electrogravimetry is nothing but the same gravimetry what you have learnt in your college as a gravimetric analysis. You would have done, many of you would have done in your pre-university or college level, the gravimetric determination of metals. That is used for the determination of milligram quantities. Let us say you want to determine aluminum, and you have to precipitate aluminum in such a way that it is quantitatively removed from the solution by carrying out a chemical reaction, which will produce a salt of sparingly soluble characteristics, and then you filter it and weigh it. That is the normal gravimetry. In electrogravimetry, what we are going to do is we are going to carry out the same reaction, but we are going to remove the analyte, that is the metal ion of interest, from the solution by applying electric impulse, and the metal ions will be reduced to metals, and the metal ions such reactions take place at the cathode, and once it is reduced, it sticks to the cathode. So, in electrogravimetry, the metal ion will be moving towards the cathode. At the cathode, there will be a reaction reducing the metal ion to metal, and the metal will be deposited on the cathode. So, the weight of the cathode will increase, and the difference in the weights of the cathode should be proportional to the quantity of the ion present in the solution. That is the basic fundamental principle. Now, in electrogravimetric analysis, what we are dealing with, it is the deposition of an element electrolytically on a suitable electrode. So, we are practically avoiding most of the filtration, okay, and also co-deposition. In normal gravimetry, there is always certain amount of mechanical drudgery involved, because you have to precipitate, you have to make sure that everything is settled, and first you remove the clear solution and then filter it and then collect it on the filter paper, burn the filter paper, make it almost ashless, and you take the difference between the weights, and it is a sort of mechanical drudgery. It does not happen easily, but it has got its own utility also. For example, if you want to determine how much of a metal is there in an ore, there is no other reliable method unless you specifically separate the metal ion of interest from the ores, that is containing all the other elements and silica and other muck, etc. So, it has got its own use, But in electrogravimetry, we are avoiding the filtration because we are going to deposit it on the cathode. So, the electrode cannot be a general electrode, it has to be a suitable electrode. That means, the metal ion should be capable of getting deposited and stored safely until you are ready to weigh it. And in normal gravimetry, there will always be certain amount of co-deposition, and then some other metal elements may deposit, and sometimes coagulation may take place, sometimes co-precipitation may take place. Several other complications are essential evils associated with gravimetry. So, one has to learn a lot of chemistry to do the gravimetric analysis. Here what we do? We are avoiding filtration, we are avoiding co-deposition. Why co-deposition is avoided? You should think about it. I will give you a 2-second pause, 5-second pause after I ask such questions. So, okay. If you have got the answer like what I am going to tell you, that means you are an intelligent person, all right. So, co-deposition is the deposition of other elements under the given conditions. So, when one element is being deposited at a particular voltage or current, then the any other element that can deposit at the same voltage only can precipitate. Such conditions are very rare in the electrogravimetry. Therefore, essentially what you are going to do is almost specific determination of the metals. So, this is one of the greatest advantages of electrogravimetry. So, an electrogravimetric technique gives you the specificity, that is very important, because no other metal ion will be precipitating under the given conditions with the same amount of voltage, because for every element deposition voltage and current are different for each element. So, it is almost specific now. So, this is it is a characteristic of the element that we want to determine. It is therefore, the electrogravimetric analysis is based upon Ohm's law and Faraday's laws of electrolysis. Okay. So, what is Ohm's law and what is Faraday's laws of electrolysis? We will try to understand now. Now, Ohm's law states that the current I, the current designated as I, is directly proportional to the electromotive force, that is potential, also known as potential EMF, and inversely proportional to the resistance. So, I can write I is proportional to E by R, or I can say I is equal to E by R. So, A is a unit of current in amperes. A is the symbol for amperes current, which will cause deposition of 1.11. What is 1 ampere? We are going to define the ampere now. So, 1 ampere of current will cause deposition of 1.11800 milligrams of silver or 0.32925 milligram, 0.32925 milligram of copper from respective solutions of their salts in 1 second. So, that is the definition of ampere. So, the current I, this is the unit for I. Okay. So, what is ohm? Here we have written resistance R, that is EMF, this is current. So, we do not call it amperes and this thing, but now we also define a unit called as ohm defined by this symbol. We write the ohm as this symbol. This symbol is the unit of electrical resistance. I have given you the current designation as A, and ohm is the unit of electrical resistance, which is defined as the resistance caused by 14.4521 gram of mercury contained in 106.300 centimeter long column of 1 square centimeter cross sectional area at 0 degree centigrade. This is also sort of definition and very useful for day to day purposes. We say resistance of any system can be so many ohms, means you must understand that it is the electrical resistance that is defined as the resistance caused by 14.4521 gram of mercury or contained in 106.300 centimeter long column of 1 square centimeter cross sectional area. How these numbers have come is there is a certain requirement which is described in the textbooks. I recommend you to read it, and I am not going to explain to you, but this is a very practical unit of the ampere. I certainly recommend you to read how this definition has been arrived at. And V is the voltage, that is EMF, a unit of electromotive force. And what is the V? It is the difference. We call it volt. What is 1 volt or 10 volts, 440 volts? You are all familiar with the voltage. Most of our households run on 220 volts. That is the electromotive force that is entering our house through the electrical wires, etc. Sometimes we use 110 volts in foreign countries, and in India and other countries we use 220 volts, and 400 volts and 440 volts are also in use for high electric current movement. Okay. So, the volt is also very useful quantity, and it is the difference electrical of the electric potential required to maintain a current of 1 ampere through a system having resistance of 1 ohm. What does it mean actually? We say it is you cannot see them. You see ohm resistance you cannot see, and then ohms you cannot see, and the current amperes you will not be able to see them. They are all electromagnetic forces. So, we have to depend upon the sort of definitions and some other alternate measuring techniques to determine all these numbers whatever we are talking about. I said 220 volts. So, where is 220 volts? Nobody writes 220 volts, isn't it? So, 220 volts means you must understand like the definition now. It must generate a current of 1 volt should generate a current of 1 ampere. So, 220 volts should generate a current of 220 amperes through a system having resistance of only 1 ohm. It's like that we are able to visualize what is 220 volts, what is 110 volts, etc. So, we also define another term, that is Coulomb. It is the unit quantity of electricity passing when 1 ampere current flows through for 1 second. Okay. So, whenever I pass a current of 1 ampere current for 1 second, I say 1 coulomb of electricity has been passed through that wire. Okay. So, that is another definition you should remember. It is the unit quantity of electricity passing through when 1 ampere current is flowing for 1 second. So, the weight of the element, it is what is the job of the current? The job of the current is to reduce the metal, isn't it? So, how much of the element is reduced? So, if I know if I can calculate how many coulombs are there, coulombs of current I am passing through. So, the weight of the element liberated when I am passing 1 coulomb of electricity is called the electrochemical equivalent of the element, that is 107.880 gram of silver. This is a choice made by the scientists and very much in use. So, what does it mean? To liberate 1 gram equivalent of the silver, that is what is 1 gram equivalent? What is the equivalent weight of silver? It is 107.880. So, if I want to liberate 107.880 gram of silver, I would say that I am liberating 1 gram equivalent of silver. Now, to liberate 107.880 gram of silver, I have to pass 96,493 coulombs will be required. I have to pass that much of current in coulombs, 96,493, and that is what it means. Now, you will be surprised to know that the same 96,493 coulombs will be required to precipitate any element in its equivalent weight in grams. So, suppose you want to liberate sodium. What is the atomic weight of sodium? 23. So, 96,493 coulombs are required to liberate 23 grams of sodium. And if you say copper, 1 gram equivalent of copper you should know. So, to determine that, we need to pass 96,493 coulombs. So, it is a very simple straightforward law, that is definition of Coulomb. Now, we are going to talk about Faraday's laws of electrolysis, and there are 2 laws. One is, it states that the amount of substances liberated at the electrodes of a cell are directly proportional to the quantity of electricity which passes through the solution. Okay. So, this is a sort of one's observation and intuition. If I say I pass more current, more will be liberated, correct. So, if I pass less current, less quantity of the substance will be liberated at the cathode and the cathode weight will increase. So, it is a general observation, but verified scientifically since last 200 years that this is exactly what is happening in an electrochemical system. So, the amount of substance that is liberated at the electrodes of a cell is directly proportional to the quantity of electricity. Suppose you pass 96,473 493 coulombs, 1 gram equivalent will be deposited. Suppose you pass half of that, that is approximately 48,246 coulombs, you will be getting 107.880 divided by 2, that will be approximately 53.44 gram of silver. Suppose you still reduce the current, you will get still less silver deposited. So, that is one thing. And second thing is the amount of different substances deposited by the same quantity of electricity are proportional to their electrochemical equivalents. What does it mean? The amount of different substances deposited by the same quantity of electricity are proportional to their chemical equivalents. That means you do not have to pass all the time 96,493 coulombs to find out, you can to find out the how much of material is deposited. You can calculate. Now, only thing is you should know the atomic weight of the substance. Now, atomic weight and this quantity, that is 1 coulomb, are closely related, because 96,493 coulombs will deposit 1 gram equivalent of the substance, and 1 gram equivalent of the substance is nothing but the atomic weight of the substance, any element. We are talking mostly of the metal determination in electrogravimetry 99% of the time. Okay. So, there are certain terms, technical terms used in electrochemical cells. What are those technical terms? You should be familiar with. Here are they, here they are. So, a cell, we define what is a cell. A cell is nothing but a beaker, something like this. I have a beaker here, glass beaker. I have two electrodes dipped in a solution, and this is connected through a battery and a resistor, and that completes the electrical circuit. So, I pass current from battery to the anode. This is known as anode. This is known as cathode. Okay. So, this arrangement is called as a cell. So, what does a cell consist of? It consists of 2 electrodes in one or more solutions. I can have one electrode in one beaker and another electrode in another beaker, both of them connected externally through a wire, and a battery system and arrangement to pass electrical current. Okay. So, the definition says you require 2 electrodes, and both electrodes may be in only one solution, or each electrode may be in different beakers, but connected from outside by a external wiring. Now, we define what is known as voltaic cell. What is a voltaic cell? Voltaic cell, or it is also known as galvanic cell. So, both of them are the names of the scientists, Volta and galvanic cell. Yes, it says the cell supplies electrical energy to the external system. So, that is a voltaic cell or galvanic cell. That means, this cell will generate current and come here and put it in the battery. So, the current will be generated by a chemical reaction going on in this beaker, and then it will come here. From here electrons will be generated and electrons will be moving here. The energy will be stored in the battery. Such systems are called as voltaic cell or galvanic cell. Basically, what happens is, in all such systems, chemical energy is converted into electrical energy. These are all basic terminology you should remember in all our future discussions, because I will simply say that it is a voltaic cell, it is a galvanic cell, it is a normal cell, like that I will be talking about, and I will not be elaborating on such systems, but if you understand this, you should be able to immediately visualize what I am talking about. Okay. Then I can define an electrolytic cell. So, an electrolytic cell works when electricity is supplied from the battery to the from an external source into the cell. You remember here, remember this figure. In this figure, the battery will let out the current and a chemical reaction will take place. That is an electrolytic cell. In galvanic cell, the chemical reaction will generate electrons and that will be stored in the battery or a cell. So, basically you are very familiar with batteries in cars, and you are also familiar with batteries in watches and torch cells, etc. We are talking about the same thing. They all supply certain amount of current, approximately 1.2 volts, 1.6 volts, like that, different quantity, and that battery is the receiver of energy if it is a galvanic cell, and it is a giver of energy if it is a electrolytic cell. So, the same cell, I can have the same cell functioning both ways. Sometimes I can use it to collect electricity into the battery, or some other time I can use the stored energy again to let out, to carry out certain chemical reactions here. So, both of them are possible, both types of uses are possible. So, this statement is true. The same cell may function both as galvanic cell or an electrolytic cell depending upon your requirement. That is, for example, a storage cell. A storage cell is what you go and buy in a shop. In the storage cell, you go there and say, give me 1.5 volt battery, everyday battery, or a Nippon battery. There are so many battery manufacturers around, and you can buy that, or you can buy a battery for your scooter, car, and many other things. They are slightly heavier and bigger. They supply more electrical energy. We are going to talk about the batteries later in another unit in the same course, but for the time being, that is known as storage cell. That means it can store electromotive force, electrical energy, EMF, in a given battery, which can be tapped to take out the current whenever we want. And when the battery completely gives out all the stored energy, I can make it a galvanic system in which electricity will be put into the same cell. So, reusable alkaline batteries, you must have heard, they are in the market. So, such things are capable of functioning as galvanic cell as well as electrolytic cell. So, if the current is switched off, what happens? The products tend to produce the current in the direction opposite to the direction in which electrolysis current was passed. Okay. Now, imagine a system like this, it is going on, and I switch off the current, stop the reaction. So, then what happens? If the current is switched off, the products tend to produce a current in a direction opposite, in the opposite direction. So, the amount of current that flows again is given by Ohm's law. So, E applied, that is EMF applied, minus EMF coming backwards is equal to IR. So, this expression holds good. So, we define what is known as cathode and what is known as anode. So, a cathode is one thing, it is an electrode. What is an electrode? Again I give you a 5-second pause. I have been talking about electrodes, cathodes, etc. And what is an electrode? What do you visualize when I say it is an electrode? So, you should remember that whenever I am talking about an electrode, I am talking about a wire. This is a wire, this is cathode, it is a metal wire, and anode is also a metal wire, but it need not be wires alone. It need not be a very thin section, it can be a plate, it can be an object like your coffee cup or something like that. It can be a metal plate, it can be cylindrical, it can be circular, it can be squarish, it can be anything, but it is a metal piece, okay, that receives the electrons from the solution or gives out electrons into the solution. So, that is a cathode. Okay. So, electrode at which, what is a cathode? It is a metal wire dipped in a solution at which reduction takes place. At the cathode, reduction takes place. That means, wherever reduction is taking place on a metal surface in an electrolytic cell, we call it cathode. So, there are a lot of people have confusion regarding anode and cathode. What happens at anode? What happens at cathode? Are electrons released from the anode or from the cathode? So, it is important for us to understand that what exactly happens. Now, if you remember, cathode is the positive terminal and negative terminal in a given system, and there the reduction occurs. Now, if what is reduction? If a metal ion becomes metal, metal ion means it is charged. If the charge is removed, that means reduction has occurred. If the charge becomes less, then it becomes a metal ion. So, that process is known as reduction. So, iron ion is Fe2 plus. If the 2 plus is removed, that means if I put 2 electrons in that, iron Fe2 plus will become, electron is minus. So, 2 minus I am adding. So, Fe0, Fe0 represents iron metal. Okay. So, an electrode is one at which reduction occurs, it is attached to the negative terminal of the source. By that way also you can identify what is an electrode, and electrons leave the source and enter the cell at the terminal. Okay. So, in a galvanic cell, cathode is the positive terminal, galvanic cell, but in the electrolytic cell it will be the other way around. So, what is an anode? Anode is also an electrode, that is a metal piece. It may be of any shape, cylindrical, wire, round, circle, plate, etc., at which oxidation occurs. So, it is the positive terminal of the electrolysis cell and negative terminal of the voltaic cell. This I have already explained to you. Okay. So, when oxidation takes place at the anode, simultaneously a similar reaction reduction must take place at the cathode. So, both these processes occur simultaneously, they cannot occur independent of each other. Okay. It is like a coin having both sides, head and tail. So, we also define another term known as polarized electrode. A polarized electrode is one when its potential deviates from the reversible or equilibrium value. What is reversible or equilibrium value? Again I give you a 5-second pause, try to think of the definition. Okay. So, equilibrium value or reversible value is what is a calculated value of the electrode. So, if the calculated value is different from actually what you measure, then we have if they are not same, then we call it polarized electrode. Okay. It is said to be depolarized if a compound lowers the amount of polarization. Okay. So, we have learnt what is cathode, what is anode, what is electrolytic cell, this thing, etc. Electrolytic cell, what is galvanic cell. We only have to learn about the current density, that is current per unit area of the electrode surface in amperes per square millimeter of the electrode surface or per square decimeter. We can do it either way. This current density also we are going to talk quite a lot in our discussions. We will continue our discussion in the next class. Thank you very much.